So just look at the problem. What it is saying? It is saying that suppose x assumes only two values which are supposed to be fixed, namely x1 is going to be equal to 1, x2 is going to be equal to 2, and there are two values for what? There are two values for estimating yi equal to say beta times xi plus ui. For a moment, let's get rid of the intercept term because we can always suitably change the data to make it 0. So, we are going to estimate this equation with what values of x? x1 is going to be 1, x2 is going to be equal to 2. No further crowding of x1, x2, x3 needed, only two values of x1 and x2. But there is a distribution of the error term which is given to us. What is that error term saying? There are the u1 which will be of course associated with x1 that can occur, and there is a u2 which can occur with x2. But when u1 occurs, u1 doesn't have a unique value. Theoretically, the setup that we have seen, it has a range of all possible infinite values around 0. But we need not really bother about that. Let us consider a case where u1, the shock term which is going to be there associated with x1, will be either minus 1 or plus 1. Similarly, the second shock term that we are going to observe when we pick up x2 and fit it into the regression, it is going to have only two values, minus 2 or plus 2. And if you look at these four values, these are called the joint distribution of u1 and u2. Again, if you want to extend this, generalize this, imagine that even only for two values, there are infinitely possible values for u2 and there are infinitely possible values for u1. So you can write them, list them, but that is only nothing but crowding of the data. Essential point can be seen even with this simple numerical example. And what we have taken is, again for the simplicity, as if they would look like fixed normal, fixed uniform distribution, we are saying that all of them are equally likely. Not a very restrictive assumption. So, what does it mean? u1 can take either minus 1 as value or you can take plus 1 as value. So, both u1 and u2 have fixed values, namely u1 can take either minus 1 or plus 1. But when u1 takes value minus 1, there are two possible values which u2 can take. It can be either minus 2 or plus 2. Similarly, u1 can take plus 1. Again, it has got associated two values of the u2, again minus 2 or plus 2. So, if we look at all possible ways in which the 1 can occur and in probability cells, what would it mean? What is the possibility of u1 taking value minus 1? Whatever be the u2, that means minus 2 or plus 2, we should add them and therefore we will get 0.5 of u1 taking value as minus 1 and again 0.5 of u1 taking value plus 1, because we have summed up over all possible u2 values that can jointly occur. These are typically called marginal distributions. Similarly, we can also think of marginal distribution of u2. u2 can take minus 2 as value, but associated with that would be u1 value either minus 1 or plus 1. Both these taken together, total probability of u2 taken value minus 2 is going to be again sum of these two, that is 0.5, and same argument here 0.5. So we have got the marginal distributions of these error terms. Why are they necessary? Because we want to calculate what will be the expected value of u1 and what will be the expected value of u2, and if we want to answer that, all that we need is, if u1 can take two possible values, there must be the probability associated with each of these values, including all possible situations of u2 taking some values. What are those? They are precisely 0.5 and 0.5. Same is the argument true for u2 either. That means expected value of u1 would be equal to either it takes minus 1 or it takes plus 1, and the probability of it taking minus 1 for taking into consideration all associated values of u2 is equal to 0.5, and for 1 also it is 0.5. So this will be my estimate of expected value of u1. Evidently minus 1 and plus 1 will annihilate each other, their probability weights are identical, therefore it would be equal to 0. In a similar way, I can argue that expected value of u2 will be equal to whatever value of u1 takes, it can take the probability of it taking the value minus 2 is 0.5, plus 2 is 0.5. That means I can write this as minus 2 times 0.5 plus 2 into 0.5, again 0. So as you can see, we have got u1 and u2 as two random chalk terms whose expected values are zeros. Now similarly, you can calculate what the variance would be. Because we have got the expected value, subtract that expected value from each possible values, subtract the difference, find out the difference, square them, sum them, and you can notice what the value of variance would be for each of them. Evidently it would be equal to 1. Okay? So in fact, this is something which is very akin to what we get in normal distribution, where that is standard normal distribution, where the mean happens to be 0 and the variance happens to be 1. Having done this, now let us look at the second part of the problem that has been given. So this is the information given to us. And what is the problem? The problem is there is a proposed new kind of an estimator that has been given. Now observe this estimator a little closely. It says beta hat. The reason we are calling it beta hat is because it is not same thing as the OLS, which we will denote by beta, which is there in the equation that we want to estimate. We don't know what the population parameter is. Our estimator is saying it will be beta hat, and how we are going to calculate beta hat? It is going to be xi into yi summed over divided by summation xi square. You can see that this is in fact fairly closely related to OLS estimator. OLS estimator is typically making adjustment for both numerator and the denominator. To use a statistical classical language, we adjust for their means. So if we make correction on the adjustment for the means, this term typically has an adjustment like summation xi into yi minus n times x bar y bar. So this is a product term, and this is a product of means, and we are doing it for n values, so n times that. This is what we call covariation. In the older notation that we had employed for this purpose was something like this. Now similarly, now this whole thing divided by n will give you covariance, and if you look at the denominator, it is summation xi square. If we were to apply the same kind of correction factor, because we are measuring all this around mean, then we can apply the correction factor, then it would be n times x bar square, again divided by n. It gives us the variance of x, and earlier notation we used to uncorrected sum of squares, we used to denote it like this. So instead of having these correction factors, this correction factor in the numerator, this correction factor in the denominator, if we use this as the method of estimating slope between y and x, can this estimator be having the so-called desired sampling distribution properties? Meaning thereby, can we say that if we apply this estimator repeatedly for all possible samples and take the mean of all those possible samples of beta hat that we get, will it be equal to beta? If it is so, then we will say that beta hat, that means this formula, is an unbiased estimator of this unknown parameter. Now similarly, doing it across all possible samples would mean that results would vary from sample to sample. So from sample to sample, we will get different values of beta hat. But if we take expected value, it will turn out to be beta. So we will in that case call it unbiased. But what about the variability? Because if the sample results vary, that means if the beta hat for all possible samples vary, there will be a variability of beta hat associated with the expected value of beta hat itself. And that's what we call the variance of this estimator. That means if estimator means this formula. If we use this formula, it will generate different values of beta hat for all possible samples. And if the beta hat generated for every sample taken in their expected value turns out to be same as beta hat, we call it unbiased. But they are going to vary. And what kind of a statement about that we can make about its variability? The variability would be the beta hat is going to have a variability. Is that variability small or big? But obviously when we say small or big, it has to be in a comparative sense. So it is small or big compared to what? And typically we compare that with the OLS estimator that we have, where this correction factor is applied. So just to understand the problem, please keep in mind that typical beta with OLS is going to be summation xi yi minus n times x bar y bar, and the whole thing divided by summation xi square minus n times x bar square. So we are effectively comparing this as a formula of estimating slope with this as a formula of estimating slope. We have already seen that this turns out to be unbiased estimator. We are in this problem therefore required to find out whether this also turns out to be unbiased or not. Secondly, we have a knowledge of how much is the variability associated with this formula, that means OLS formula, and we should have some way of computing the variability of beta hat from sample to sample. And if we estimate that variability, is the variability associated with beta hat smaller or greater than the usual OLS estimator? This is what we mean among all possible estimators, among all possible linear estimators. OLS gives you the lowest variability, and one which has got a lower variability will usually be more preferred kind of estimator, therefore preferred kind of formula. And that's the argument for preferring OLS over other competing estimators. So please understand, in sampling theory you can have several estimators and you would be required to in fact choose which of them is desirable. The two usual more frequently employed criterion for this is A, they must have unbiasedness, or B, they must have the variance which is as low as possible. It is possible in some cases where the estimator is not necessarily unbiased completely, but it must have known direction of bias, whether it is upward or downward. But if it has a lower variance, so there would be situation where some estimator whose direction of bias and the size is known, but if its variability is lower, sometimes that kind of estimator or formula can also be preferred. So please bear in mind, these are not necessarily conditions that must be fulfilled at the same time. If they do that, even better. But there could be situations where it would be required to in fact consider the possible trade-off between if the bias is there, but the direction and the size of bias is in some sense can be judged, can be known. And over that, if we find that the variability must be least because we want the greater degree of precision in the nature of forecast or the generalization or what we call universe estimates that we want to build up. In that case, it is possible that in some cases a biased estimator, in the sense of not being unbiased, but with a minimum variance, can also be sometimes chosen. So this is the basic idea of choosing appropriate formula for estimation. That means choosing appropriate estimators when applied to the idea of repeated sampling. So it is in this view you are given this problem: derive the distribution of B hat, beta hat. What does it mean? What do you mean by deriving a distribution? Deriving distribution means you must be able to compute and claim the expected value of beta hat, and you must have some way of estimating the variability associated with beta hat. And please understand, by the very same formula, from where is this variability coming? the variability is coming not from x, but it's coming from y. Why? Because y contains error term. That means this variability from sample to sample, for any estimator, whether OLS or non-OLS of this type, will be coming from the random term. So there is some connectivity between why beta hat varies from sample to sample. It has something to do with the way in which random terms contribute its impact to y. So we should be able to derive distribution of beta hat, means we should be able to talk about expected value of beta hat and check whether it is equal to unknown population parameter beta. As compared to OLS, is the variability of beta hat from sample to sample, estimated variability of beta hat from sample to sample, is it lower or higher than the OLS beta? This is something which has been actually the focus of this problem. And given this limited data of only two fixed values of x and only two fixed possible values of error terms, how this can be done is something that we are going to see when we deal with this problem. That means when we derive the distribution of beta hat and check its unbiasedness and estimate its variance.